Me to walk.
All right, 7:30, so we'll get started. And if people come or leave, that'll be fine. I'm not gonna stand for that. There we go. Good afternoon, everyone. My name is Ethan Hoban. I'm the president of our chapter of HKN Eta Kappa Nu, which is the IEEE Honor Society for Electrical and Computer Engineers. And this is our Tech Talk series. So this is the third talk this semester. And we have Sean Mitchell here from Cummings Aerospace to do a talk on counter unmanned aerial systems. So we got some good stuff coming for this evening. So I hope you all be engaged and have some good questions for Sean to answer. Otherwise, I'll let him get to his intro. And if you haven't signed in yet, please do. And then at the end, there'll be a little sign out where you can basically give feedback or request topics for future talks. We have a lot of contacts across the street. So with regards to any topic you may be interested in, we can probably find a professional to come and speak to it. So if we get enough people requesting a certain topic, we'll generally find someone to speak to it. This topic that we're doing today was one that was requested last semester. So I'll pass it off to Sean.
There we go. Okay, so what we're doing tonight, we're going to talk a little bit about unmanned aerial systems. It's a rehash if any of you showed up to the first UAS lecture we did last semester. But we're going to expand upon that. We're going to talk about the stuff you need to know, so if you didn't see it, you didn't miss anything. It's about UAS and counter-aircraft systems, a little bit of aircraft survivability, and talk about the complexity of the counter-UAS problem, and then get into probably why most people are here, which is the weapons of counter-UAS and some of the ways you take down a drone. We'll talk at the end a little bit about countermeasures and why this is a cat and mouse game perpetually now, and have some questions answered at the end. A little bit about me. I've been here in industry for 8 years now, give or take. I'm a lead software engineer at Cummings Aerospace. Professionally, I do a lot with robotics, AI, ML. I have a lot of experience with controls, navigations, comm systems. Currently, the project I work on is a high-speed, low-cost, multi-role fixed-wing SUAS that actually does some counter-UAS stuff, so I have some experience with that. Double A from UAH in 2020, minor in CS, and I'm finishing a master's probably in summer now, but maybe still this spring, and I have a thesis there at the bottom. So if you see that thesis come through your feed, and you like AI stuff, come by. Just a disclaimer to keep me out of the jail, basically. I've worked with some of these technologies, I know things about them, but everything in here comes from books, what's available on the internet, practical experiences. I'm not giving you anything that you couldn't easily get or learn outside of an office, but a lot of what makes this subject interesting is classified CUI type stuff, so we don't get to go super in-depth with everything. So starting off, defining unmanned aerial systems. They stand for unmanned aerial systems or uncrewed. It's a family of air vehicles whose primary attribute is they operate without a crew, so they're completely autonomous or have some level of autonomy, remote control. They can do anything pretty much a crewed aircraft can do, and then some. And that's pretty useful because human pilots, the price to train a human pilot varies plane to plane, but between $1 and $10 million kind of captures a lot of what the Air Force does. $1 million for a cargo plane, $10 million for the nice planes. Drones, on the other hand, are extremely cheap. I saw you can get some on Amazon for $9. I don't know if they work, but you can buy them. And the robots can perform tasks that are too dangerous or impossible for humans. That's kind of the big selling point with robotics, always has been. So kind of just some word dump here. This talks about the history of UAS. Goes back to really the late, mid-1800s. Austria was using unmanned balloons to carry bombs against Venice. Don't recall why they were at war, but 1800s, everyone was doing it. And that's kind of the first recorded use of remotely delivered weapons that aren't a catapult, something kind of flying. Towards the 1900s, those early experiments with radio-controlled aircraft. World War I and II, we start seeing countries developing, aerial torpedoes that are pilotless, things that are radio-controlled. World War II saw the first unmanned combat air vehicle. I think that was the U.S. that made that. And then, start seeing radio-controlled aircraft used for training, for gunnery practice. Cold War, obviously, drones became more popular. It kind of had to be, but initially they were mostly reconnaissance platforms. We hadn't really reached the point yet where they were useful for full tactical, like strike missions. Mostly ISR, Vietnam, China, that type of stuff. So, going past the Cold War into now, pretty much everyone here probably knows what a Predator looks like at this point. But planes like that had become key portions of the U.S. military and tactical and strategic theaters. Originally a reconnaissance platform, later became armed. Pretty much every country now has something similar and hundreds of models. You also saw civilian and commercial UAS really emerging because sensors, autonomy, and affordability made it possible to make $9 quadcopters you can sell on Amazon, buy at Target, that type of thing. And then because of that, in addition to military applications, it become critical to agricultural mapping, emergency response, logistics, research. UAH has a lot of people who work in UAH rotorcraft, and the aerospace and mechanical departments have people that do drones. I think electrical has a few guys that do it. But it shows up, you'll see ones used in farming for getting soil to, health and, crop health. And, when they try and have disasters, they're able to deploy communication networks, stuff like that. So these are kind of everywhere now. So, and this kind of just talks about the categories of UAS. People kind of associate a drone as a drone, but as we've got to the modern era, we've really started making subfamilies that are not just based on size. I mean, we have the group 1, 2, 3, 4, but a lot of these now can break down into stuff like micro, nano, small UAS, and the micro UAS are under a quarter kilogram, low altitude, short type applications. Some of your little FPV drones that fly around in buildings can do that, up to like tactical UAS that can be 8 to 24 hours, 600 kilograms. The MEL and HEL stuff, the high altitude, medium altitude, those can, be 10,000 kilograms. They're 50,000 feet. I mean, that's, like Global Hawk there, for example. Loitering munitions, which are interesting. I've worked a lot with those. One-way strike, pop-up tactical, precision effects. Switchblade, if anyone's familiar with the Switchblade, is that. Cargo logistics, again, medical delivery, the Amazon drones, that type of stuff. And finally, counter UAS. Which, if you notice, has a variable typical mass and is low altitude, short endurance. And we'll talk a little bit more about that. So, counter UAS, kind of an interesting subject. These are systems, not always drones, but a lot of times they are now, designed to stop an unmanned aerial system. Typically, these are deployed against enemy assets, but police and other forces use them to. Stop has a lot of meanings here. Probably what everyone is immediately thinking is blowing it out of the sky, but that's not necessarily what it always is. In general, it refers to the ability to stop it from completing a designated mission. So this is a part of a broader family of CUXS technology, which includes anti-ground, anti-submersible, anti-air. This is a whole family of technologies and techniques, and there's a lot of overlap. Taking out a drone with CUAS is a lot of those same technologies do apply to taking out like a UGV or submersible. I guess applies in space to a degree, but no one's really doing that yet. So since they're still aircraft, and we're kind of focused on the aircraft tonight, we probably should talk about some approaches to stopping an aircraft in general and what makes an aircraft survivable and how that all works. So jumping into that a little bit. This is kind of a brief history. I like my history slides. I apologize for that. Of counter aircraft technology, going back to World War I and II. Starting in World War II, planes start happening. People realize we need to do something about it, and you basically get modified field artillery and machine guns aimed manually at an aircraft. So you see point gun at plane, and shoot at it. With the interwar and World War II periods, you start getting specialized anti-aircraft guns, mechanical fire control computers, radar. And eventually into World War II, radar-guided anti-aircraft artillery, proximity fuses, things like flat clouds, and eventually centralized command systems that enable coordinated air defense networks. And that becomes a big thing. Cold War gives us surface-to-air missiles. Everyone loves those, unless you're on the receiving end of one. Advanced radar guidance, jet aircraft countermeasures, and C2 infrastructure. Again, the big thing is as we go forward in time here, counter techniques involve coordinated networks and layered defenses. 70s and 80s, same thing. You get mobile missile systems, increasing digital electronics and radar resolutions, automatic engagement systems. So if something happens, the human is only on the loop, not in the loop, and layered air defense strategies. 2000s, 2010s, more network sensors, new radar techniques like phased array, integrated air defense, and then now you're basically at, the focus of counter aircraft is countering stealth, UAS, hypersonic threats, a lot of multi-domain sensing, rapid data processing, high precision interception. We're getting into the smart munition stuff. So this kind of is where counter-aircraft at a glance has evolved from, but quite literally from simple artillery and machine guns to, missiles that see you over the horizon and take you down before you even know you've been saw. So, people might have seen this picture before. It goes about in a few memes there, but this is talking about aircraft survivability analysis, and it's a pretty rich field onto its own, and it goes back to the early days of human flight. It basically gets broken up into three metrics for aircraft survivability: survivability, susceptibility, and vulnerability. The picture on the right is from World War II, and it is an image showing bullet holes in aircraft that landed from combat. And the working theory at the time was those areas needed reinforcement because they'd been shot at. So clearly, you reinforce those. Well, the page is called survivorship bias, basically, and what they didn't take into account is the planes that came back with those bullet holes were the planes that came back. So maybe the weak points were not the red holes, maybe it was the other places because those planes didn't come back. So that leads into the theory and kind of the why you care about studying aircraft survivability. So survivability, starting with that, basically is a metric of the capability of an aircraft to avoid or withstand a hostile environment and complete its mission. So, can you survive doing what you need to do? That's kind of a mathematical probabilistic sum there of, probability you get hit and the probability you get hit and you get killed. Susceptibility affects the chance you get hit, and vulnerability affects the chance you get killed from it. Kill here also can be, preventing the mission from actually being completed. Some of the design levers you have to improve survivability, you can reduce your signature, your radar cross-section, your IR acoustic visual signature, make yourself harder to see, tactics and maneuvering. Obviously, if you're very clever or you're very agile, harder to, you have a better chance of surviving the encounter. Various countermeasures, electronic warfare, decoys, and structural hardening and redundancy. If your plane is built like a tank, probably better than if it's the Wright Flyer. But the overall goal of survivability is to reduce the probability of a mission loss. So from there, we get susceptibility. Susceptibility is the probability that an aircraft can be detected, tracked, engaged, and hit by a system. So this is not do you survive, this is what are the odds you actually get hit. And what drives this is, again, your radar cross-section, your signatures, emissions, kinematics, countermeasures. Basically, the goal of this is you want to reduce this down. You want your probability of getting hit to be way down, because when you do that, that sends your chance of survival to go way up. And from there, you also have vulnerability, which is basically a conditional probability of the aircraft being killed if given a hit. So this is where you get into you've been hit by something, someone shot you, your fuel tank is leaking. Does that actually kill you? So, overpressure from a blast, fragmentation, penetration of critical components, fires, etc. And this is where you have mitigation strategies, armor, shielding, your redundant systems. If you have two engines, what are your odds of surviving better than a plane with one engine if one of them goes out? And the answer is actually pretty good. But basically, the goal of vulnerability is to ensure that the mission continues or that it can be recovered after a hit. So that kind of gives some terms and scopes of how do we view aircraft in a way that can be countered. So going from there, what makes UAS really hard to counter? What makes all of this a massive field that has a ton of research? Well, UAS are just different than aircraft, even though they're quite similar, because by design, UAS and drones want to be a little bit simpler. They have low RCS, they tend to be very small compared to a full aircraft. You have big drones, but you also have way more that are small. The one I work on at work is about 2 or 3 feet long. That's not aircraft sized. So, and if you apply good design techniques, that RCS is already low, so it even gets lower. Weak IR signature, minimal acoustic signature. At night, an Apache has a much larger acoustic signature with its rotors than a quadcopter does. They can also utilize very low altitude flight. An aircraft with a human does not probably want to fly 2 feet above the ground. Quadcopter does not care. It is very happy to do that. So you're not able to look at something in the sky and go, hey, it's coming out. It's like, no, it's crawling across the floor at you. Highly maneuverable. I don't know if anyone has seen the quadcopter parkour videos with them flipping and doing all the inversion and those inverted maneuvers, but normal aircraft can't do that. Whether they can, humans can't, not without turning to goo. Oftentimes, there's very short engagement times in typical con ops. A lot of these drones, some of the loitering munitions, some of the solutions like that, do not live long. Some of them live for, the time of a missile, a couple of minutes there. That's quite a bit different than an aircraft that's, circling over the sky all night. So your engagement time might be 10 seconds to deal with that problem. So their vulnerability is non-trivial because in general, they usually have distributed electronics. You think of a quadcopter, you have multiple rotors, you have multiple, ESCs, you have sometimes have a computer in different places. All those have control loops, and there's no pilot. The human fragility constraint is gone. So you can kind of do what you want to do. And on top of that, soft killing, jamming or taking it down that way, can actually fail pretty easily against autonomy, vision-based guidance, pre-programmed missions. If you turn off your outside sensors and just say you're going to that one place and you have vision, navigation, and some autonomy, what good is jamming if it loses the communication link? So, this kind of puts you already in a place of, the only way to assuredly counter UAS is to, hard kill it or bring it down in some capacity. You can't just distract from it. So it's also a really interesting asymmetric optimization problem. If you assume that the attacker cost per platform of the UAS of interest is $100 to $5,000, and the defender sensor plus the interceptor is, I don't know, I want to say tens of millions, hundreds of millions there. I don't know what some of the new systems are, but they're not cheap. That's not really you took down a $100 drone, but it cost you $1 million. Is that smart? Oh, and then the swarm case there, what happens when, they've spent, $100,000 for $1,000 drones, and now you have to do this, and you get overwhelmed and saturated. The swarming of all these things just makes a expensive platform not viable. So even effective solutions fell under saturation, basically. And there's issues with stuff like magazine depth. If you have 1,000 drones coming at you and you have a kinetic solution that shoots bullets, do you have enough bullets? Or if you have a direct energy solution, do you have enough power? Are those capacitors charged enough? Do you have enough sensors to handle discriminating 1,000 different drones? And if you do, is there a human on the loop there that can make that decision effectively, or is your entire network infrastructure reliant on, floods of data? So, top of that, there's a lot of reasons that the UAS are hard to counter. This threat space evolves fast and much faster than traditional aircraft procurement cycles. It's almost analogous to cryptocurrency versus the stock market. It happens much, much faster. A UAS designer can just change signatures, autonomy stack, alter behaviors, decoys, swarms. That can happen. I know at work we have been set there many times and gone, oh, this piece doesn't fit. 3D printed a new piece and we're able to build the drone in another hour. So, it's that easy to make changes. That's not so easy on a full aircraft, especially one that has to have people trained to use it. On top of that, counter UAS spans a lot of fields. It spans radio frequency, kinetics, direct energy, cyber warfare, AI perception stack. I mean, it's everything is involved in this. So it's a constantly moving target, no pun intended. So basically, the bottom line is the defender has to increase his susceptibility. Remember, that's basically, are you going to get hit of a target that's physically small, has a low signature, can be terrain masked, and is constantly adapting and moving. It also needs to increase their vulnerability. So what the chance that it actually gets a kill of a platform that is cheap, distributed, and often completely expendable in military terms. And really even just normal layman prices, it's a very coupled optimization problem. So that's why people put a lot of energy into this, and people really care about making this work well. So, what do we do about that? I guess I just kind of skipped a slide there. So moving on to kind of the weapons approach. I guess I left out a slide. There's basically a handful of weapons that get used here. There's, kinetic weapons, there's directed energy, there's electronic warfare, and then there's also now like cyber warfare, and it's kind of a modification of the kinetic stuff. That was supposed to be a slide between 22 and 24, so that's my bad. But basically, kinetic weapons are exactly what you think they are. They're bullets, they're guns, they're missiles. They are things that physically transfer a momentum or structural loading onto the target to induce a loss of flight worthiness, which is to say, if I shoot your wing off, you're probably having a bad day. It's traditional, but it's still really effective because it's, again, planes without wings don't fly. They can, but that's mostly just how much engine you want to put on the back. So to start with, some of the things you see are direct hit interceptors. Hit to kill utilizes pure kinetic energy via collision. So we just run into it. You don't really even need a fragmentation or blast. Even a sub-kilogram interceptor at 1 to 300 meters per second can completely shear rotors, fracture propellers, induce avionics displacement, shift the center of gravity, which basically just says, if I throw a rocket at you at 300 meters per second, you're probably moving. You're probably not having a good day either. And, if you have something bigger, then, that's a whole problem. So moving from there, you have things like proximity fragmentation munitions, frag rounds, basically. Instead of having a direct hit, these can utilize fragments via cloud dispersal when they get close to it. So, you don't have to necessarily hit your target, but you have to be in close enough that a proximity fuse or something says time to detonate. Sometimes they look like, soup cans that have layers of tungsten shards, basically. So when they blow up, they expand outward in a cloud. They can also have, you have the radial approach. You have stuff that's a forward propelling jet. There's a few optimizations you can do there. I'm not a warheads guy. I just have done some of that. But they're very small, 1 to 5 millimeter, and you get radial velocities of 2,500 meters per second, upwards of that. That's usually enough to damage most things. Sufficient density to sever rotor blades, batteries, damage flight control boards, but basically that's really a bad place for you to be around. Have gun-based systems, pretty self-explanatory. Heavier autocannon type stuff. Flat clouds, things like that, high explosive incendiary rounds, things like that. But basically just, shoot something large at it. And you also have, machine guns. We've seen that in Ukraine, the ability to just, see a Russian drone and just fire machine guns at it, like the Shahid and all that. It's relatively, it works. It's not great. You're basically playing probabilities of if I shoot enough bullets in the air, does the drone get hit? Missile-based kinetic interceptors, again, this is literally just a SAM, essentially, can induce fin separation, wing snap, propulsion shaft misalignment, and IMU shock, which is a nice way of saying if I hit you with a missile, you're probably moving a lot, and I guess your main propulsion shaft is now misaligned or missing. These scale poorly to counter swarm. So if you have a high-value drone, something slow, maybe this is a good choice. But if you have to launch 1,000 missiles, then I've won that fight. I can send you 1,000 drones for cheap. I've won that engagement there if I can make you burn, $100 million of missiles in 10 seconds. So this one's fun. Net-based kinetic capture. I bet that's something people don't really think about, but it's a non-destructive kinetic method. Basically, a projectile or drone deploys an entanglement net, which, again, quadcopters and drones in general don't like having nets around them. Aerodynamic drag spike. These often include parachute deployments or tethered recoveries. They also make these for guns. I've seen a few companies selling rifles that shoot, basically like kind of a net launcher type thing. These are great if you want to capture the drone. Again, what I was saying of stop does not always mean kill. Stop sometimes mean get that drone down and recover it so something can be done with it. And then, of course, the fun one of ramming UAS. These are a little bit different than just kind of the pure kinetic ones, but this is essentially what it sounds like. It's an interceptor trying to hit another interceptor. Because these sometimes don't have explosives, usually they are actually purely kinetic. They're pretty minimal collateral damage. You're not blowing anything up. They do support recoverability, and you can actually do reattack. I saw a really nice video on LinkedIn. I want to say it was Lockheed or Raytheon had posted it recently of a drone they had deployed in a test, and it hit the drone, bounced off, flew back around, came back, and was bouncing off of it a couple of times, and then eventually, the target drone succumbed to, death by 1,000 cuts. Disadvantages of this is, you do have to make a nice drone to do this. You're not doing this with the $9 Amazon quadcopter. If you do, then you probably should start a company because you'll make a lot of money very quickly. There's a big autonomy requirement because you're essentially in a hyper-complex terminal guidance scheme for, like seconds and minutes trying to do that. And you need a lot of ISR quality tracking. You really need to be able to know what you're looking at, what you're trying to do, and where stuff is. But the reattack is a big plus one. So moving on to some other more interesting stuff. This is where we get into Star Wars stuff. Directed energy weapons. There's only a couple of really categories of those that you're kind of seeing. deployed, but the first one is high energy lasers. It's essentially what you think this is. This is, we take a pinpoint laser, like a laser pointer, put a unholy amount of energy into it and burn a hole through your drone. They couple optical energy into a small aim point on the target, cause localized heating, structural weakening, battery thermal runaway, or control failure. And if I punch a hole through your engine with a laser, you're probably not controlling it well. This is a fundamentally time-on-target weapon, which means that it's not instant. This is not Star Trek. It does not blow up instantly. There's actually quite a few seconds that it has to be on target on that particular point because it is a heating element, basically. The performance of these systems degrades significantly depending on environmental conditions. It's pretty nice as a concept, but shooting lasers through obscured terrain, dust, clouds, rain, anything with reflection, refraction, all that fun stuff. If there's chaff or something in the air that's a active countermeasure there. The other thing is you usually see these on places that have the power plants to support it. So you see it for like base defense. You see them about like cruisers and aircraft carriers now that can support them, the nuclear power plants. You see some mobile ones now, but they're usually like, you know, a truck with a bunch of batteries and capacitors pulling a trailer with more capacitors with this on top of it. And they don't, you know, they don't really have a long lifespan. You know, you can't fire at something for 2 minutes. You know, kind of the alternative is, and you know, to note here with higher energy lasers is it's a single target thing. You're not shooting all the targets at once. This is what you do if you want to shoot all the targets at once. Use high-powered microwaves. This is that Leonidas system that was recently started kind of making the rounds. But basically, you're just hitting pulsed microwaves towards something, and that causes a lot of electronic upset. You know, as opposed to trying to burn through something, you're trying to essentially corrupt the electronics and really mess things up there. You know, clock instability, bus corruption, voltage breakdown. You know, you're introducing electromagnetic effects into the target drone. So it's much lower precision. It's an area of effect weapon, basically. If you have a swarm of 1,000 drones, it's actually a great way of dealing with all of them at once. But it's expensive, and like all directed energy things, you're directing a lot of energy into the air, you're doing transduction, you're losing a lot of efficiency. And it's indiscriminate too. So if you have something flying in that space, then you also just EMP'd them too, basically. So also have these things. You have dazzlers, which are not particularly new, but are kind of interesting. These are not designed to kill, but essentially to disable and distract. They're essentially like the equivalent of shining a laser pointer at an aircraft, you know, flying above your house, which you should not do. That's a crime. Putting it in there for CYA. But these essentially saturate like EOIR payloads, blind sensors for SLAM and optical flow, and just deny ISR terminal guidance. You know, if you're using vision or a sensor to see me and do something with me, if I shoot a laser pointer in your eye, you're not doing that anymore. I mean, you can try, but you know, this supports the ability too for having a counter UAS engagement without a kinetic effect, which is a polite way of saying if you send a drone at a ship, they might do this first and sink your drone before they shoot a missile at you just to be polite, because you know sometimes that becomes like an act of war if you just start shooting at aircraft that aren't yours. So from there, you have electronic warfare, and we have some great videos. I think they're in the appendix there that we have done as a group there about this. But you know, basically the idea here with electronic warfare is you're trying to attack a communication link or some type of telemetry link there. So you can do noise jamming. We have videos, like I said, that go into this more detail, much better than I could ever go into. But if you put enough noise in the air that your communication link or telemetry link no longer works because it's saturated, essentially the power of the jammer is too much, there's a lot of interesting behaviors that are enabled by default or people use in drones. It's very common to have a fail-safe return to home, return to launch if your communication goes out. Sometimes you will see, I don't know what to do, so I'm going to stand still in place, I'm going to land. Or if you're really lucky, it'll be a link lost flyaway and it will just go do something and go live its best life without you. So this is actually a pretty effective way of doing it. Noise jamming is not necessarily the way because it's just basically screaming into the electromagnetic void. But what you also can do is you can do GPS, GNSS denial, since that is a big part of electronic warfare now. Small UAS often lack full redundancy for navigational systems, because having a full nav pod, it can be big, it can be very expensive. Expensive gyros, INSs are, can get into the millions of dollars easily. So we don't put those on disposable drones. We might put a simple GPS from Adafruit on there, and that might be fine. But if you block that out, you get navigational drift. You can also get a geofence violation response. A geofence is for a drone basically a bounding box of you have to operate within this altitude or this XY coordinate. And usually there's a automatic response of you've left it, go back to that. So, if you make it think it's somewhere it isn't, then it may just leave. Also has autonomous termination logic. Sometimes when things get lost, they, will basically just self-terminate, fly into the ground, detonate a payload. That's sometimes safety, that's sometimes security of you don't want your drone to end up in someone else's hands, so it can be anti-tamper. So, some of this stuff can use the safety and anti-tamper of a drone against itself, which is kind of interesting. You can do protocol-aware jamming, which is kind of like broadband noise, but this one selectively targets specific elements of your C2 link, so target synchronization, control uplink time slots. Basically, the example I use is attacking a Mavlink connection on a plane. If you know that Mavlink requires, heartbeats to keep track of what's on the GCS and your plane to make sure that's a valid telemetry communication link, if you do something that disrupts the heartbeat, the handshaking, any of that stuff, then it won't have, any command control, which is super useful. So from there, we evolved to cyber warfare, which is actually pretty interesting. You can think of this if classical electronic warfare in this context is denying a communication link. Cyber warfare is owning the link. It's taking it over. This is the equivalent of hacking a drone. I tried to keep this one a little more vague because telling you many consumer and prosumer drones use unencrypted telemetry, static pairing, and known behaviors and predictable frequency doesn't mean that the curious among us can probably become a problem pretty easily. But this stuff is out there. It's pretty easy to figure out too. You're essentially performing a man-in-the-loop, like RF attack on an embedded system. And once the command's taken over, you can force a landing, redirect to the capture zone, disable a payload, crash the whole firmware, even turn the drone against it. If I take over your drone, then, if that has a bomb, then yeah, I might just use the return to launch button. That might be something I care about. You also do a lot of other interesting stuff there. You can spoof GPS. So instead of removing the navigational truth, you can replace it. So, and that has a lot of interesting implications. So by transmitting a counterfeit PNT, which is position, navigation, and timing solution, you can do course deviations and stuff like slow captures, where I just, over time, make you think you're somewhere you actually aren't. And maybe that somewhere you actually are is, my landing field where I'm going to capture that drone. You can, again, trigger the geofence. Precision land at an adversarial selected target. Again, I can just slowly make your drone think that it's going home, but its home is now at my home. If I'm like an enemy asset, lots of stuff you can do with data link exploitation. Again, many ISR and C2 payloads use very common formats. UDP, all of these are very standard web protocols. There are lots of ways to violate and do stuff with them. It's definitely possible to compromise the video stream integrity or command layer, and you can get crazy with this. You can inject your navigation waypoints, turn off systems, just delete the whole mission, rewrite the mission. I mean, if your mission was to bomb me, it's like, nope, you're going to go bomb something else now. That's completely possible if you can get into the drone and do stuff with that. So, why do we need to do all that and have all those techniques? Well, because as fun as it is for us to make really sophisticated guns like, butterfly nets, they also get to adapt and work on their side too. So, this is countermeasures. We won't talk much about this because that's probably a lecture unto itself, but it's worth mentioning. And these focus on basically preventing of the counter UAS from working. Some of the things you can do that, prevent some of these previous weapons we've talked about, that help mitigate it on the drone side. If you do jamming or anything that tries to block it, vision navigation, sensor fusion, sun star tracking, local AI ML as part of your GNC flow. If I try and keep you from moving and try and do anything like that, try and convince you are where you aren't, if I take out that need for external stimulus, or have something that's objective like the position of the sun, that can completely negate, some of the GPS spoofing. Stuff like motion injection, thermal signature shaping. It's very easy to, in your flight path, have something where you've introduced a stochastic wobble into your flight that's still stable, but from a radar cross-section or something that's doing moving and tracking, that suddenly disrupts everything, because everyone's kind of thinking, oh, the plane flies upon a stable flight path. That's how crewed planes work. Well, because these are controlled by computers, they don't need to do that. They can wobble and look like something that isn't, and that looks really weird on a radar. That looks like a bird or something like noise. You can do thermal signature shaping, where you control, heat exhaust, things like that, or you can make drones that, don't use turbojets. They can use electroducted fans, things like that. You can include your own dazzlers and chaff on your drone. It is perfectly valid if they shoot a laser at you to shoot a laser back. You're just not going to have the same power of laser, but you can do dazzlers that affect their systems. Swarming is also a great way. If you have 100 of you, the odds are in your favor. You can do things where you randomly adjust the RPM of your propellers to confuse Doppler tracking. If it's looking at sound and airwaves there, if it's not a consistent 300 RPM thing there, if it's plus or minus 25, you can still control that. But from a sensor classification perspective, that's going to look, again, the wobble effect. Stuff like mini repeaters to counter fire control tracks. They're, basically kind of spoofing and jamming of its own. You can do link layer authentication for C2, where it actually tries to do proper handshaking, proper security, proper hashing. Mission locked autonomy, which is basically when that mission begins, nothing takes it out of it. There is no fail-safe. I say go outside of the room and it goes, and if it loses all of its sensors, it's still going to do that. Redundant links and protocols. In general, you should not rely on one single communication style, one single approach. Your C drones that might use, something over UDP, something like a MAVLink or a TAC network, but also may have an optical sensor that shoots a laser that says, here I am in a bad scenario. Electronic shielding, in general, if you're going to get hit with something that's directed, maybe don't try and do your best to make it protected. And sacrificial components, this goes back to, aircraft redundancy. If you have multiple engines, multiple fuel tanks, multiple batteries, if you lose one, you're not in quite the bad place that you think might be normally. So, and just a little bit, some food for thought here about CUAS in practice. These systems do not work alone. If you go and you are doing a CUAS theater and you bring just one of those systems, it's probably not going to work well. And the odds of you actually picking the right system for the drones you're going to be seeing is low. On the right kind of is a very busy chart there, but I can attest, I was at an industry day this week there with some military folks there that were basically showing how drones are supposed to work with this, and they had 30 or 40 different types of drones with different missions and altitudes and sizes and deployments and timings and all that. So, counter UAS in general has to be a layered defense. This is where I was talking about the network systems of the old and that development. You don't get to just put one down, everything gives sensors and data to everyone, and, there's a lot of coordinated timings. You'll see, multiple systems being deployed, against the same target. So you get redundancy with this. It allows for you to defend against a wide variety of quantity and types. And systems like this, you'll see short, medium, long-range UAS, and you'll have ones doing ISR, ones that are just communication relays, ones that do hunter killer, interceptor, different payloads, different, whatever you'd have it. There's a lot of money to be made in this. So, that there. So, if this interested you, as we wind down there, I guess I moved through that kind of fast. If all this interested you, Huntsville is a great place to work. Don't leave. Most careers in this town involving UAS, which there are a lot of them, include some aspect of CUAS. I have not worked a job in my career that touched UAS that didn't have some CUAS aspect or consideration of how do we handle that. Even if you don't work directly with UAS, a lot of people I know, work on CUAS that are ground-based, rifles or basically hard-point anti-aircraft guns, things like that. They go on ground, naval, even manned aircraft. You'll see some of these systems making their way to like an F-35 or something with a modular platform. again, even if you don't touch CUAS2, CUXS is also a rich field of its own. So, and most of these techniques still apply to that as well. And, you know, if you like this, you know, get your security clearance. Don't do things that make you lose your clearance, because a lot of the really interesting stuff is behind the closed doors. When you look at pictures like this and realize that that's, you know, supposed to be the enemy, there's a vested interest in, you know, not putting out, you know, our best and, you know, latest weapons there to people like me that can talk about it at tech talks there. And if you were interested in some of what we did here too, that YouTube link has other lectures we've done where we've talked about like electronic warfare and vision-based navigation, GNC, embedded programming, all of that. But we have many full lectures about it. If you thought the electronic warfare stuff was cool, we have multiple on that. We had an EMP lecture, I think, was that in January? Mm-hmm. Yeah, in January. So if you like the directed energy stuff, don't think anyone's done anything on a lot of kinetic weapons yet. I don't know if we're allowed to do lectures on warhead design here. Have some citations. There's some other links to books. And
did you cite me, bro?
Yeah, because you did the lectures there. I cited myself too. I'm on there. Yeah. So as acknowledgements, UAH, IEEE, Ethan, and we'll do questions if we wish there. And there's a nice sign out page.
Let's give it up for Sean.
Definitely sign out.
Yeah, real quick, if you have time, just fill that out. Just recommendations, anything you want to hear more about, that kind of stuff. And it helps us with metrics, you know, keep these going. And yeah, let's open it up for questions.
No questions. Wow. I must have explained that really well. Okay, that's
I have one. I'm just trying to figure out what a slider was on.
Flip through the slides backwards.
You know,
it
the
was
topic.
like the microwave.
High power microwave?
Yeah.
Here we go.
So I had an interview, and they classified these as cheap with like quotation marks. I was wondering if you could tell me a bit more about that, because that doesn't sound cheap. So I'm wondering like what that's being compared to. Like what is that cheaper than? Like what's the alternative?
It's like a nuclear missile, probably. Yeah, I know.
Yeah, so for high power microwave, when they refer to cheap, it's on a shot per shot basis and cost. So is that physical system rather expensive? Absolutely.
Yeah.
But once it's in place, so that like the Leonidas system, you know, it's tens of millions of dollars. But once it's physically there, the shot per shot is just power.
Yeah.
And it's not like it can effectively wear, let's say, a missile. You want to intercept 20 drones.
20 missiles.
Normally you need 20 missiles. That very rapidly, 20 missiles could easily be $10, $20 million in one go.
Sure.
Which means you've already blown past one emplacement of these. But assuming they're close enough, one of these could take out those 20 drones for a couple $1,000, probably cheaper in straight power. Mm-hmm. But, you know, there are trade-offs. These things have limited range.
Yeah.
And you can harden your vehicles against them. If I'm, again, as some countermeasures, as he was mentioning, countermeasures, from a high-power microwave perspective, there is a such thing as shielding. So if you want your drone to beat something like this, you can shield it, just increases cost.
Yeah.
At the end of the day, war is actually just who has more money, or who has cheaper weapons who do more damage. Battle of economy. But yeah, so when you hear things like cheaper, like cost per shot, it's basically how much do they have to spend to shoot your bullet, right?
Gotcha.
And how much do you spend to send your bullet?
Thank you.
So if we're interested in like this career or something similar to it, and we kind of wanted to be proactive on projects, like what does a project look like for something like this when we can't necessarily make like
You're allowed to make a lot more than you think.
just
You're allowed to make stuff you don't advertise too.
Yeah, if you don't record it, no one's going to catch it.
Yeah, if you don't go on LinkedIn and say, hey, I made a counter UAS system and I tested it in my neighborhood, the Fed won't come and get you most likely.
And just so you know, this is important to note. Even if you buy the $9 drone off Amazon he mentioned, the second that drone takes off, regardless of how cheap or crappy it is a FAA regulated aircraft, and even you are not allowed to shoot it down. Doesn't matter what you do.
Really?
So you can take a lot of flack. Will they come after you for shooting down a little drone 5 feet in the air? Probably not. Can they? Yes. So be worrisome about that.
Also, fly drones, it's probably worth, doing the diligence of, maybe consider getting your 107 and being a legal drone pilot there. Just so you don't have the double illegal drone pilot plus illegally shot down your own aircraft when they come for you.
Like projects and stuff, if you specifically are talking counter UAS things, your options are, well, if you want to go against UASs, the most important part of taking down a drone is tracking and acquisition. So you can build sensor pods, like you could make a turret, but instead of having an effector, like an actual gun or something on it, it just makes use of cameras. Fun fact, you can purchase very nice radars for about $200 that are very useful. You can make it use radar, you can make it use a camera. If you get fancy, you can try to do thermal tracking. Drones make noise, you can use microphones for acoustic location, that kind of stuff.
You can get some thermal cameras pretty cheap from Adafruit too. They're not great, but you can get some basic ones that hook up to Arduino and give you enough to get a couple of pixels on target there, which gives you your basics of IR tracking. So.
And the best part of building a sensor pod is it can do more than just track a drone. That might be your application. But if you make the pod small enough, you can put it on the drone, and now you have a kamikaze drone, right? Like, you can do some cool stuff.
You should not test that if you make it.
You can make kamikaze drones, actually. That's fair play.
Is it? Really?
Yeah,
I
funny
guess
enough.
so, yeah.
It's allowed to shoot itself now, apparently.
Have to go hit like a...
Don't put explosives on it,
Yeah,
though.
hit like a
Just make
scarecrow
it
or
kinetic.
something. Yeah, the bounce off of it. I watched a video of a couple of Anduril drones hitting a tank, and they were kinetic, and they just like hit it and just like kaboom and bounce off it. There was a demonstrator system, but it's kind of an interesting approach there. Simulation is also a good way. Learning how UASs and drones work. Period. If you like rotorcraft, if you like fixed wing, but learning how those work. But also, you can do a lot with simulations. You can easily, if you put some time into the physics of it, learn the basics of doing, like a tail chase interception type thing. There, you can easily, get into that. And that's the only cost is time. It's not computationally that expensive, and you won't get in trouble for that. But again, if people don't know you're doing something. If you're looking for things to help your resume, sims are nice.
The best thing from a project's perspective is to simply build something. Most people will not. So it's a good thing that puts you ahead.
Hardware makes you look good because it shows you invested some money, you invested some time, and you made something.
Yeah, in the age of today, as he said, I've heard it even from investors now that they're less likely to even look at software-only service stuff because of how cheap it's become. Cheap. People can pass off. People who historically couldn't make something now can make something. If it's good, great question, but often, you can't tell that very easily. So anytime you build something physical, even if it does have a software component, because it will, you can't avoid that.
Yeah.
It is still more impressive if you can do the other stuff. Do some little basic 3D modeling, do some integration, that kind of stuff. That's good.
I guess it also helps if you like this type of stuff. There's a lot of room, like I have here. You could get into RF, kinetics, or Moorhead design, thermo, directed energy, electrical engineering, software, cyber. I mean, there's no way to. It's pretty much everything you do can probably come back to this. If you like making nets and throwing nets at things, you can do net stuff. So,
You mentioned time on target for high energy lasers. Is that is CW or ultrafast more popular? Do you think?
I think a lot of lasers, the CW, right? Isn't that what they're
Most of the
pulsed?
time, they're not really pulsed anymore.
Are they CW?
Yeah, most of the time.
Yeah.
Pulse only makes sense if you have a really high power pulse.
I knew
Because again, the time on target
was pulse. I thought like the microwave was a pulse system. I
Yeah,
thought there,
the
but
time on actually that one's also not really pulsed anymore. Even
I thought it was.
I mean, it can, but
Well, I mean,
yeah.
I'm sure it can, but I thought
The issue with the laser stuff from a pulse versus CW perspective is most assets won't even fall from a single pulse. So you either need to keep pulsing or hit it with CW. A lot of the older systems are pulsed because that was all they could do. But we've drastically improved optics and electronics to the point where we can afford CW now from a power and heat budget.
Yeah.
So they're becoming more CW.
Time on target and all that is such a big deal, especially when you look at with some of the kinetic interceptors. I talk about the IR sensor there. You have that same pixel on target that is really kicked on there. Is really will make or break. Like if you can actually hit something. Something I've seen a lot of is trying to do your nav solution in such a way that if you're doing an interception, you're doing a telechase, because you get more time to track and have time on target this way than if they're both coming. And you get half time versus double time, basically. So all of these really do rely on, excluding stuff like this or like flat clouds, the ability to, focus in on a target for a length of time for one purpose or another. Okay.
Do you happen to know very much about the circuit design for some of these radar techniques? I have a lot of borderline unanswerable questions, though.
I was like,
Everything's answerable. You said circuit design for the radars?
Just some of the radar techniques, yeah.
Okay. Do you want a block diagram?
I was like, he's the radar guy.
I honestly don't know what kind of answer. I'm just kind of.
So when we're talking radars, right, a lot of people might think of, well, if you've ever been on a plane at an airport, all U.S. airports have the standard air surveillance radar. It's that red tower with the parabolic reflector rotating. Yeah, we don't use that crap anymore. It sucks. It's good enough for large, slow airliners in a known location. For something as small as a drone, it probably can't even pick it up.
Yeah. Especially if it's like wobbling and doing all
Yeah,
the
modern
kind of
radars are what are called active electronically scanned arrays. So where you guys are probably familiar with these dishes spinning, they don't need to do that anymore. Nowadays, we have physical arrays of potentially thousands of antenna elements physically standing still. They don't move.
Yeah.
That's
like
the
this.
front of that's a Eurofighter.
That's a
Yeah.
Eurofighter. Disgusting.
So basically, you can't see it super well, but this is a slot radiator array where each little tab is its own full antenna, and they're controlling each antenna with its own full transmit and receive radio.
You can kind of see it's a sum of transmit receive to each antenna aperture.
And basically, the point of this is so you don't have to steer it. You can use principles of constructive and destructive interference to basically form an invisible RF beam.
Yeah, there you go.
So yeah, that's the F-22. Yeah. That's the F-22's ESA. So each of these notches is an antenna. And basically, the functional stuff behind this is it's a full radio per element, and then you have some overall control scheme, often just a computer. And the radios themselves often can do the signal processing, but fundamentally, if you're going to try to make something like that, you have antennas, you have the ability to control the amplitude of the signals at each antenna, and you have the ability to control the phase, that's why they're called phased arrays, of the signal at each antenna. Now, you don't actually need to have a full radio per antenna. That's only if you're trying to do a full, like military-grade, actively electronically scanned array. Instead, you can feed the same signal to all the antennas and then just control phase and amplitude shifters on each line. A lot cheaper. We're talking on the order of, you went from $20 million to $200,000, like way cheaper. Because instead of 4,000 radios, you only need one. All right, so it scales it down.
Yeah.
But yeah, so let's click this one right here. So this is an ESA block. Active electronically scanned array. So zoom in a little bit.
There we go.
These are your levels. This is the computer, the whole digital beamforming. This is when it decides which signals to send. This is all digital, it's all in bits. Then we hit a digital analog converter. So now we're in actual signals. We're at the RF domain. You have this block called a digital up or down conversion system. Sorry, the converter's right here. I guess they're doing this first, which is a little weird. But when you do up or down conversion, everyone knows what sample rate is, right, for the most part. If you want to reconstruct a signal, you need to sample it. That's what's known as the Nyquist rate, also known as 2 times its frequency, whatever that is. Not too complicated. It has to be above that or you risk aliasing and other issues. Well, the problem you're going to run into is these radars are not operating at 200 megahertz. They're not operating at, a gigahertz. They're almost always operating at S-band or X-band, aka 2 to 4 gigs or 8 to 12 gigahertz. That's very, very fast. Sampling that means double that frequency in terms of sampling. That exists, it can be done, but why if you don't have to? And the answer is you use this, a down converter or an up converter. We have circuits that are capable of turning low frequencies through mixers, convolving, that kind of thing, into higher frequencies that have the same content. And then when we receive the high frequency back, we strip the high frequency carrier out and go back to the low frequency. This is the basis of most radios. So this is just a fundamental step. Once we've done that, in this case they do it digitally, then we translate this back to digital, or back to analog, and then on receive it goes from analog to digital. This is the analog up and down conversion, so there's a whole other step. This is where they actually bring it to the super high frequency. This is an intermediate digital thing. It's a little harder to explain right now. And then the whole analog beamforming, you can see where they have amplitude and phase shifters here. That's what these signals are for. And then this is just a transmit or receive block. That's what that indicates. And that just goes.
So you're doing like frequency modulation with the carrier wave when you're sending it out and producing it?
If that's your purpose, yeah. You'll do that in the signal. The modulation almost has nothing to do with the radar part of that. That would just be, I mean, that's a part of it, and you should modulate, because if you're just sending out sine tones, you're like hilariously easy to jam, because that's very easy to replicate. There's a whole thing about what are called jam-resistant waveforms. That's a whole classified concept, but which is fancy waves that you can't easily copy and send back to jam them, right? But the whole point of this is it's just taking, you want to form a beam in X direction, so you send a whole bunch of this data all to these antennas at once and control them simultaneously. The frequencies and modulations is just a property of the signal. From an ESA perspective, that does matter, but in this context, the thing that matters more to actually aim it and direct it is amplitude and phase. So it's just controlling these two things. It looks simple, these are actually very expensive. A phase shifter chip, like an integrated circuit, you can just buy them. About $90 per antenna.
Really?
They're very expensive.
Can you get one DigiKey? Like DigiKey has them?
Huh?
Can you get one DigiKey?
Doubt it.
I was like,
I mean, whenever you go higher frequency, they get more expensive. Yeah, see, they get bad really quick.
wow.
What frequency are those?
Uh,
It doesn't say immediately.
9 to 12.
Yeah, so that's X-band, so that's dead, and like, this is exactly radar level. So this is, they're selling this for radar design.
Buy 10, you get them for 2,700. Buy 100, you get them for 24 grand.
So most of the radar techniques frequency range is in the gigahertz.
Yes. Does radar operate super low frequency? Absolutely. But the physics of the rules of wavelengths for resonant elements, let's say you're making an antenna, generally, an antenna should be about half a wavelength. You can go higher, but it's not necessary. We like our antennas small if we can. Standard rule is half a wavelength. Well, let's say 300 megahertz, that's an easy number. Its wavelength is 1 meter. So at 300 megahertz, it means your antenna is 50 centimeters, or half a meter, right? Like roughly 1.5-ish feet. That's not small, but it's also not huge. So we have antennas and radars that can do what's called over the horizon, which means we blast energy reflected off the ionosphere, and then it bounces back down so we can see past the curvature of the Earth. The problem with that, yeah, there they are. These are really cool. Raytheon's the primary. Yeah, but here's the problem though. Take a look at that.
That's the Russian one, the woodpecker.
Yeah, that thing's horrible. But
Yeah, it is, but it's cool though.
the issue, as you can see here, is this is rather large.
It's just a little large.
And there's no real way around that. Once you go past, 300 meg and you're going down, like this is probably like 100 or 50 megahertz. Now each element, and again, they use arrays as well. Same trick, just not necessarily phased, but same trick. Each element's like 10 feet long. So it becomes a problem. I will note, however, these systems are so-called anti-stealth. Stealth aircraft cannot hide from these. Your radar cross-section increases as your frequency decreases because the wavelength, as your vehicle reaches a certain multiple of the wavelength, you get resonant and it produces very strong reflections. So an F-35 can be relatively easily spotted with something like this. But why do we use higher frequency then if this is so good, besides the fact that the antennas get big? Well, it's because as the wavelength gets bigger, your certainty as to where something is also gets bad. So I have people I work with who are in the Navy who use these, and they told me, yeah, when we would pick something up, we'd be like, yeah, it's somewhere here. So we're talking hundreds of miles of search area. So it's not super helpful. So these higher frequency things can like locate you to a centimeter, whereas these low frequency things can see you across the planet, but with a unacceptable amount of imprecision. So in reality, stuff like this, from like a kill chain perspective, these are so-called early warning. They tell you, hey, something is probably in that area. You deploy ships, planes, whatever. They use the better stuff to search their smaller areas to try and locate you.
And you see that with like even radars that are not like this too, of just you have a detection radar and they're a tracking radar that has a higher fidelity of, hey, there's something, turn on and look in that direction, and because, you know, then you get the best of both worlds of easy detect, easy track.
Another trick is the higher frequency you go, the worse the energy propagates through free space. The atmosphere attenuates it worse. So what happens is, as he said, you could still have like an S-band radar that's 2 to 4 gigahertz, and then an X-band one that's 8 to 12. The X-band one is actually responsible for shooting the missile. The S-band is for broad search because the S-band has a longer effective range. So he's helping precisely identify where things are coming from, and then when it's shooting time, the X-band one just shoots to where we know they're at to precisely locate them.
Signed you out. Yeah, it's crazy.
Did it?
Yeah, it did.
It's a little weird.
Yeah, sign in.
You said detector size was half the wavelength normally?
What's that? Okay, we're still good. Don't touch anything there. Huh?
You said the detector size is normally half the wavelength?
For an antenna, yeah. So, for example, if you're talking, so 300 meg, this is just a trick for radio stuff, 300 megahertz is 1 meter. So 300 meg is 1 meter, 1 millimeter is 300 gigahertz. So in that range, you can kind of visualize half of each of those, right? So 300 gigahertz, your antennas are minuscule, it's half a millimeter. Good luck with that. As I said, energy attenuates as you go higher frequency. So when you start, do these things exist? Absolutely. Do we use them on Earth? Not really, they're in space. There's no atmosphere up there, so there's no attenuation. We can do what we want up there. Common radar, as I said, there's S-band, X-band, so 2 to 4, 8 to 12. If you guys were to say, make the project we mentioned, make a tracker and purchase a radar, you're not gonna get a phased array one. So any radar you do make, you're gonna have to gimbal the thing. But those radars for commercial use and so-called like automotive use, because a lot of self-driving cars and other cars just have those sensors in them now, those are actually far higher frequency, probably 27 gigahertz, 72 gigahertz, 92 gigahertz. Texas Instruments sells radar chips at those frequencies for like $5. Full radars just on a chip. They're very impressive. So you can actually do quite a lot. Radars are very popular. A lot of stuff. This is the most prolific sensor by far. EOIR stuff is important and is coming into its own. It's getting good, but it will never actually beat this. Passive can only do so much. Anything else? And I guess go to the YouTube channel real quick. We can show them some of the topics. Because a lot of the stuff you guys are asking thus far, we actually have full lectures on it from either me, Sean, another speaker. That's not going to get you anywhere, bro.
Well, you're right. Oh, wait.
Oh, it did. Never mind.
Look at that.
Yeah. So, yeah, scroll down. So we've got quite a lot of these by now.
We've been doing this for a little bit.
So the first one, this is the stealth, and we've done a couple of these now. So are there discussions of radar in there? Yes, but this is, you know, this whole thing was about counter UAS. Stealth is about counter radar, right? Or one of the methods of counter radar, along with electronic warfare. There's 2 talks on that. We've got Sean's nav thing. So if you're gonna, or not nav, that's a different one. Sean's nav one is over there. But Sean's introduction to automated target recognition and detection, that would be something if you were to make some type of seeker, you would want this type of information. We just have broad software stuff. This is a whole talk on radar discrimination techniques. So I mentioned how a radar works, but then there's the whole concept of someone here was talking about, oh, but what about the waveforms, that kind of thing. That's where we start talking about how that works.
Probably the last 4 are worth hitting up because embedded software is good for anything you'd be doing on a microcontroller. We have our first drone talk, the unmanned aerial system one. We did the EMP and the advanced EW there. So all those are probably worth, you know, if you liked what you saw, then definitely go through those.
Yeah, so for electronic warfare, I do recommend the advanced one. You don't actually need too much. I still did it from an intro perspective. There is the original talk that's good, but the point of the advanced one is we mentioned a lot of stuff like just jamming. Like just, you're on X frequency, so we broadcast louder to try and make you drown you out. that technique is actually rather weak. It doesn't work very much. It's actually somewhat simple to defeat. It takes quite a lot to make that work. So nowadays, advanced electronic warfare is done by so-called deception jamming, where instead of actually trying to block you out, I instead listen to what you're sending me, create false reconstructed signals, send them back. So let's say you were looking with your radar at me, and I would have emitted one signature in a certain location at a speed at some altitude, that kind of thing. Now, I can use fancy radio tech and make it look like I'm 20 planes, all different types, different speeds, different sizes, and different locations. So it makes it extremely dangerous. It's very hard to deal with. As we've mentioned, this whole talk is talking about, hey, I sent 20 drones. That's actually kind of an issue. It's hard to intercept a whole bunch of stuff at once. Well, even worse if you can't tell if it's even real. So now you're just wasting your stuff on air. And that's the power of something like deception jamming. That is like, talk about like the Venezuela stuff. Besides the fact that we basically just turned off their screen so they just couldn't do anything, but also this. It's very hard to fight against the United States. Our electronic warfare suites make it such that you think 300,000 planes are coming and maybe there's only 5. It's very hard to deal with that. So it's a good talk. There's a lot of good signal processing and radar concepts in there. A lot of electronic warfare and countermeasures for anything broadly is based around you need an understanding of how their signal processing is done and what things they're looking for, and then you simply play with that. Right? If they're looking for amplitudes, if they're looking for frequencies, you mess with it, and that lets you do some fun stuff.
Well, the fun part is you can layer all that up too. Now we have the AI wingmen. They're supporting fighter jets there. They can do deception jamming, and then also have a swarm or wolf pack behind them there. So not only do you have a swarm that doesn't exist, you have a swarm that does exist, and they're making a different size swarm that may or may not exist. And that's flying at you with guns now.
Google the MALD, ABM MALD. So this is the MALD.
MALD.
I'm not sure why Google's slow. Get rid of, there we go. All right, get rid of ABM. Just do MALD and then just missile. So this is a so-called miniature air-launched decoy system. These are in play. They were actually highly classified until we showed them off in Ukraine. So there was like a video we had given them to Ukraine, and the Ukrainian Air Force did a video.
2023.
Yeah, that's new.
Makes you think.
Yeah, we've had it for quite some time. But the whole thing, what this does, is it's capable of doing these false targets. So we send these tiny little, these are cruise missiles technically, but functionally a cruise missile is just a drone, realistically. And it can just, on its own, like we gave the Ukrainian government a couple of these, and if you guys remember back to that very large counterforce attack where they were able to take out a lot of Russian air defense and take back a huge amount of ground in like a week or two, that was because we only gave them a couple of these little missiles. That's all they needed. Because all you need to do to beat a modern adversary is just jam their radars, and their missiles are kind of useless. So that's all we had to do.
Raytheon did all the cringe posting about it too. Look at that.
Yeah, once they were allowed to.
Yeah, once they were allowed to, they were bragging about it.
Yeah, and actually, while this is very classified, actually, if you're clever, look up signature augmentation system on Google Patents, and you'll see what they're doing. Yeah, might as well. Augmentation.
Augmentation.
So they made this public for whoever knows. Type that into Google Patents instead of just Google.
Those three, is that under more?
You got to go to Patents specifically.
I don't browse Google Patents like you do.
Got to check.
Okay, you got it. Can I do next, or is that going to ask for something?
It is while my password probably in there.
Fix it.
Why does it need this for
I don't
Google?
know.
Go to
I want to know.
They probably do want to know.
Yeah.
Oh my god.
Ugh.
That's some cyber. Yeah, that's a cybersecurity there, brother. Oh my god.
Yeah, you move over a bit.
Okay.
Typing at an angle I can't do. But yeah, my passwords are very long.
It's the entropy on that one, man.
Oh yeah, bro. That's how it's done. I have to remember like 20 of these things. It's easier to do like phrases. that it needed that for Google Patents. The original one is Boeing. What? It might be subsystem.
Yes, I did get taken down after you were like.
That'd be really funny.
It's interesting. I'm actually in the physics lab working on an experiment of how you would detect something like that.
You're doing the LiDAR spoofing
I think that's what it's called.
Yep. with Blakely?
Yeah. That's it.
Yeah, it's good stuff.
That's the word.
Uh-oh.
I mean, I'm not.
Did you say something on camera you weren't supposed to say on camera?
No,
there,
I
brother?
know. I was definitely on normal Google Patents.
That would be funny.
Yeah, because
I mean, it shows up there, so.
They may have taken. It'd be very funny if they took it down.
You dug too deep.
That's not how you spell Boeing.
Boing. Oh wait, stackable unmanned aerial vehicles.
No.
Okay, I saw. Hang out there.
Something. Oh.
It's a Boeing company.
Annoying. But yeah, try to find that. Maybe they just know it's me and they won't let me show it. But basically, the whole concept is if you know the radar cross section of something, you can project it out on its own. If your physical vehicle is tiny and you have a radio on board, normal radar cross section, imagine it as a fingerprint signature. If a radar is to reflect off of a vehicle, each vehicle has a specific shape, so it's gonna reflect a certain way, and you'll be able to be like, oh, that's a F-15, F-16, whatever you want to say. If you just make your vehicle very small and just have a radio on board with a bunch of antennas in certain places, when it's your turn, when you detect a radar hits you, you can actively project signals that would have been the reflection off of a larger or different vehicle. So they're very fancy.
So it exists on the Wikipedia page for the ADM 160 mold?
Like it has the patent link.
Like the Wikipedia page, there's a link, but the page doesn't exist currently. It's like it's been nuked.
It wouldn't be. I wouldn't be surprised. But hey, it's on them. I mean, they published that patent. And you shouldn't publish patents for classified stuff. That's really not a good idea. You're supposed to do trade secrets for that, but even so. If you guys didn't know, trade secrets actually have the same protections as patents. You just have to disclose them a different way. But yeah, that's that. So if there's not any other questions, we'll close this one out. And then thank you all for coming.